Okay, so our next keynote speaker is Phil Duan from Tesla. So Phil Duan is a senior staff software engineer at Tesla. So he leads the Autopilot team for occupancy network, object detection, behavior prediction, auto labeling, and online perception. So today's talk title of Phil is Building Vision Foundation Models for Autonomous Driving. So let's welcome Phil.
Share from this. Let me figure out the hardest part of the presentation. Sorry. Okay. All right. Thanks for the introduction. I'm very excited to be here with you guys to share some of the progress we have made on Tesla Autopilot for the past few months. So for those of you who are, okay, let me actually hide this. Anyway. For those of you who are not familiar with Autopilot, this is a self-driving feature building for all the Teslas made in the world since about 2016. And the features range from basic autopilot, which has like lane keeping, vehicle following, to what we call a navigating autopilot, which works on highway for lane changes, follow the route, take forks, to our most advanced software package called full self-driving. And this basically takes you from a point A to point B with no human interventions at all. And this is the video from one of our customers driving in San Francisco. As you can see that it is capable of navigate through a complicated city, taking turns, yield pedestrians and traffic signs. And the uniqueness about our approach is that we are very famous for doing this with vision only. So all this is done with just 8 cameras around the car, provides 360-degree field of view. And these cameras runs on 36 frames per second, and it processed by 144 teraops of compute in our car. And we also do not use any additional sensor and HD maps whatsoever. And this works, anywhere in the world for basic autopilot, and it works for full self-driving with North America, including Vancouver. So, if you go to a Tesla store today, buy a car, you can do this yourself. And currently we have about 400,000 cars driving with the full self-driving software. And cumulatively, they have driven more than 250 million miles. So you can see that it's like a lot of data coming from the fleet. And for all the other cars, Autopilot is always running in the background, even though it's even when human was driving. So we provide a activity safety feature for things such as automatic emergency brake. So when human makes a mistake, the Autopilot will try to take over and protect the safety. And besides that, Autopilot also runs in the background to collect more data to help us to build our neural networks. So so there are roughly about 3-4 million cars running in the world today to do this data collection. And you can think about these are robots on wheels. So besides Autopilot, about 2 years ago, we also started to make a humanoid Tesla bot called Optimus. So this is the basically in a humanoid form factor. It has a very impressive hardware platform, 200+ degree frame body control. It is built for a general purpose robotics application. And as you can see that the robot obviously has a completely different form factor than the cars, but we were able to leverage a lot of lessons we learned to build the cars, build the compute, and build the software to bootstrap this project. And the bots are basically, robots on legs, and as I said, it shares a lot of stuff from the car. One example, it is that it shares the same compute platform. So this is the in-house built FSD computer chip with a 144 teraops per second compute, and this runs all the Teslas in the world, and also is used to power the robots. And because we have the same computer platform, it's also fairly straightforward for us to build the same AI software stack. So the Optimus and the Autopilot software team, we work very close together. We share the same repo, and when we build the computer vision models, we try to leverage things so that we don't have to build two separate applications. And this also kind of enforces us. Whenever we build new software, we have to think about, how do we build something that is foundational, that can be shared among the two applications. So one of the network I can mention is the Occupancy network. I think ties pretty well with the challenge you will have later in the workshop. So we effectively have the same network running on both the bot and the car, with just a little bit of tweaking where certain things are more relevant to cars and certain things are more relevant to the bots. Even though it is a completely different environment, outdoor versus indoor, we're able to actually kind of build a network from like exact the same model with just a little bit data difference. And I think we showed this Occupancy network the first time at a CVPR last year, and since then we're kind of very excited to see how the research community has reacted to this. We have seen all kinds of different variations of this coming out. There's also challenging with hundreds of people participating, and I'm definitely very excited to see where this is going next. But for those of you who are not familiar with this, I'll just do a quick recap on this. What the Occupancy network does for us is that it takes all 8 cameras image video stream in and produce a single unified volumetric occupancy in vector space directly. It has video context, and for each point in the 3D space, we predict whether it is occupied or not. And because of the video context, we are able to reason about occlusions and predict the things are behind visibility region. And the blue contour showed earlier here briefly was the way we use to model the volumetric visibility. And it also has a dynamic resolution. As you can see from the video here, certain voxels are bigger than the others. I will go to more details later. And for each of the voxels, we also predict semantics as color coded here, such as curbs, cars, static, road debris. Those semantics are usually defined for more driving relevant classes. And as you can see, for Optimus robot, we'll use kind of a different set of semantics. It also produces occupancy flow for motion. Since this network is very generalized, it does not make any assumptions on the object shape or motion. So it is able to capture arbitrary motion, such as a swerving trainer here. And this network right now runs in all Teslas in the world with the FSD computer, and is incredibly efficient in memory and compute. Runs about every 10 milliseconds with our it also helps with latency. We're able to remove ISP in the loop, and it is we don't even do any tone mapping at all, and all the images generated here are actually done post-process just for human eyes. We take these images and we rectify that with the camera calibration, and we then feed these rectified images into a set of RegNets and BFTNs to extract multi-level image features. Then we construct a set of 3D position queries along with the image space features as keys and values, and we feed them into an attention module. The output of the attention module is some high-dimensional spatial features. And we align the spatial features with vehicle odometry to create, to capture motion. And this is kind of like a simplified here, but it's a lot of work done happening here to just make sure the vehicle odometry is done correctly to recreate what's happening in the car and to align the features precisely. So, and after we do this, we're able to create a very rich spatial and temporal features, which we then pass through a set of deconvolutions to provide the final output for the volume, which include occupancy, flow, semantics, and so on and so forth. But the output of this volume is in a fixed-sized voxel gray, which is not precise enough for control. As you know that, when things are close by, you have to really know these dimensions very precisely, and things are farther away, probably does not matter that much. And the way we solve this problem is that we also predict feature maps on a per voxel basis. And then we feed it into those per voxel feature maps into a set of MLPs with a set of 3D positional queries. So as the output of the network, we can query any 3D positions around the car to get the output. So after knowing the model better, let's look at one more video. Here we have an articulated bus parked on the side of the street, illustrated by the red L here. As we get closer, the bus starts to move. As you can see, the front of the bus turns blue first, indicating the model is predicting non-zero velocity. And as the bus keeps moving, you can see the whole thing turns blue, and you can see a very nice shape capture the motion and the position of the bus. So this is kind of like a awkward task for traditional object detection, because you have to figure out, okay, what's the formulation? Do I use 1 or 2 cuboid to represent this bus? But for occupancy network, it does not matter. All we care about is what is visible and what is the motion. So our car will be able to actually handle and yield to this bus correctly. Besides this voxel gray, we also predict surface output. And the surface has both 3D geometry as well as semantics. So by semantics, I mean we also capture the color of the surface and all the road markings on surface, whether it's a stop line, lane lines, or like any yield signs, stop signs that are on the ground. And we found this to be incredibly helpful for driving in unusual driving environment such as San Francisco, which has a lot of hilly road and curvy road, where knowing what the surface looks like in 3D space removes the flat world assumption, and we found that incredibly improve our driving smoothness. So, and the surface or the volume are actually not output separately. In fact, the volume output is actually aligned with the surface implicitly, so that when you go through a different surface area, the voxels does not move up and down. It always just aligns with the drivable surface. And as we can see from this video here, the car is going through a hill crest area. You can see this 3D shape of the surface very nicely, and it aligns with the voxel gray as well. So we can use this for a lot of different things. For example, the planner can use this information to decide how fast we should be driving here, and also it helps us to reason about occlusions, because sometimes the occlusion is not really due to any obstacle; it's just because the lack of surface as the surface is like going down. So we kind of build this network, and it runs in the car for about, I think, probably almost 2 years now. And then it works very well. So we start to think, what else can we build on top of this? So early this year, we had this very fun project where we start to predict a distance field around the car on top of the Occupancy network. So this is literally just put a small hat on top of the network and do a regression test to get a distance field. And we then show this distance field on UI for customers as a manual driving feature for parking or maneuver through very narrow area. And this is the video with one of our customers doing a parallel parking. And you can see from the right side that this contour is generated by this distance field. So compared to like traditionally, usually this is done with ultrasonics, right? So we just most of cars have ultrasonics on the front, on the back, and trying to just measure the distance directly. And the advantage here is that first we have 360-degree coverage. Let me just play this video one more time. And then it also is able to capture the obstacles at different height because we don't have this sensor limitation. So for example, the curb, and ultrasonics is usually pretty bad with curb detection. And third is that it covers arbitrary range, right? So we don't have like a range limit from the ultrasonic sensor anymore, and it's able to basically capture according to as large as what we want from the occupancy network, and we just show as a range that is comfortable for the driver to use. So this vision-based park assist is just a small application. But while working on this, we realized that this model actually has really rich features that's able to capture a lot of things going around us. And so we start to think, okay, how can we navigate this and build a really strong world model? So if you zoom out a little bit and look at this network, right? So the bulk of the network, all it does is really just create this world model in the vector space features. And this kind of ties to the previous talk where, we really want to just build like a really nice 4D world model to understand the world. And once we do that, all the downstream tasks are actually just tiny heads that is very easy. And we can just like plug in, do some fine tune on that. It usually just works very well. I couldn't find a very nice picture to capture this, so I just put a Tesla logo there to represent the vector space features. So, but what we're really looking for from this direction is really just like how do we build this 4D space world model feature, and then we can just use that to capture everything we want for driving, for humanoid robot, or for anything that related to embodied AI. And if we do this correctly, we'll be able to use this feature to capture everything that is relevant for driving, whether it is the aforementioned, a volume or surface, which has, all the information we need for understanding where to go, and for objects, for lanes and for traffic control. And instead of trying to build different models to tackle each one separately, we really want to just like build one model that does everything together. And traditionally, we shared a lot of features from image space, which just extract the 2D information. That information is actually not quite enough for doing this kind of foundation model. And now, since then, we have changed our approach to actually combine everything in vector space, so that we just need to build one model that does everything very well, and then then connect them with different tasks for downstream applications. And in order to train such a big model, obviously you need tons of data. So we are very proud that we built this very mature data engine in the past few years. And this, in my opinion, is one of the biggest advantages we have here. So what do we do here, if you start from the bottom, is that whenever we have a model, we deploy it to the car. And then we mine the model with millions of Teslas on the road. And we mine mostly to two things. First is that we use heuristics to detect things that happen very rarely, so we can get the data back and then feed that into our network. The second is that we also run this compared to what a human does. So to understand that, okay, what is the inconsistency here? What did our model do wrong so that the human made a different decision? And once we have this event trigger, we put this data back, and then we automatically label this data to generate this beautiful ground truths in 3D space, and then we use to train this model. And we call this approach fleet learning, basically learn everything from our fleet. And most of the work happening at Tesla Autopilot is actually just crank this data engine and get the fleet learning going. And we have engineers looking at data all the time, and arguably spend more time on data than the model. And give some examples of data. We showed this video at AI Day last year, which shows how we leverage all the fleet from all the Tesla vehicles from the same intersection. We put them together to reconstruct the 3D surface and the lanes jointly, which will be able to actually create a ground truth neighbors that much better than if we were just to do that with a single trip. You can see all the lanes are very consistent across different videos, across different trips. And then we feed this data into our network to train our lane network. And the good thing about this is that our customer drives the Tesla in all kinds of different locations, and we get data mostly from the places where with a lot of Teslas. And guess what? That's also the area we care the most about. So we can immediately feed this data back to our training and train a network, deploy to the car, and the customer will just have a much better model because of their driving. And this year, we extended this same approach. Besides lanes, we start to model everything. So this is a 3D reconstruction from multiple trips of Teslas in the same area, and we put together. All this is generated from 8 cameras of video streams, and we put together through different trips. And you can see that it's able to capture all this very high quality information, and we can use that to train all kinds of stuff to make sure the world is consistent. And all this data is very rich in terms of that. We don't have a separate data set just to provide one ground truth anymore. We just have a unified data set that captures everything we need to train such a foundation model. And besides the data quality and the quantity, the other thing that really matters is data diversity, right? So if you only have, boring data, this thing will rarely work. So this is also one of our biggest advantages where we can get those data back from fleet. So this is just some examples of the random Tesla customer driving. So I will just pause for a second, let you guys to see what kind of crazy scenarios we can see here. A lot of the stuff is, when you will rarely run into in real life, but once you, aggregate over 4 million cars, it actually weird stuff happens every single day. And what we do here is that we put this data back and put in the data engine directly and run the auto-enabling pipeline, fit into the data set and the model training. Once you put all this stuff together, you'll be able to just build a very large, highly diversified, highly quality data set, and we use the train foundation model. And in our opinion, this is the path forward to build a foundation model for autonomous driving, and as well as eventually the whole embodied AI. This work presented here is done by dozens of very talented engineers at Tesla Autopilot. It's my privilege to present on their behalf. And if you guys are interested in this, please consider joining us. Thank you.
Any questions from audience? Yeah.
I know that Elon Musk has claimed that we will have end-to-end system in the FSD12, right? And I would like to know how the occupancy network you have mentioned can be changed or even fit into this kind of end-to-end system.
Yeah, so that's a good question. Yeah, so basically we're building this network. So it's not really the occupancy network anymore, right? So we're basically building this foundation model to capture this world model, and we think that will be essential to use for end-to-end driving. And as for the end-to-end driving application itself, we're not ready to show what we have done so far yet. And I guess stay tuned.
Okay, so you just mentioned, so probably occupancy network is mainly used for building the foundation models, but not used in the end-to-end system.
Exactly. Yeah. Yeah.
Hey, thanks for the nice talk. How do you compare attention or self-attention or cross-attention based occupancy estimation with traditional multi-view stereo? So like
I would say that a big fan of Transformers. So, and we've definitely tried the different approaches, and the Transformers just like works amazingly well. And it is also very resistant in terms of I'm a big fan of like learn-based stuff where the information will extract more implicitly, where for different cars, when you do multi-view geometry, it is like usually a very deep like uphill battle in order to get every tiny bit of a geometry detail correct, so that you can build everything and correctly. And this kind of stuff just works much better, in my opinion, with the attention module, which goes to play well with our strength of a huge amount of data. When you learn from most data, the model just learns it very nicely.
Cool. Thank you.
Hello, thanks. Thank you for your wonderful speaking. And I have two questions. The first is, what do you think the problem of occupancy network? For I have talked to many researchers. They think the occupancy network are too dense. The feature or something are too dense and too heavy to do, and every disadvantage of segment model, the occupancy model also shares the disadvantage. So what do you think the problem or disadvantages of the network of the occupancy network, and then there is a question too, and what is the next after occupancy network? Yeah, I have to.
Yep. So there are basically quite a lot of different representations for like this occupancy, right? So we use kind of dense voxel gray, and you can also do any other representation, implicitly, SDF, this kind of stuff. So the as I described in the slide, basically we have this dynamic resolution thing, which is a way to help us to make the network actually small enough to run in real time, right? So we don't just like naively say, okay, we need X centimeter resolution, so we have to segment the entire world in such thing, which is obviously not scalable. So I would say that the dynamic resolution thing we did here is one of the main reasons that we're able to actually achieve a high perception performance while running incredibly fast and efficient. And a lot of advantage we have is also with our own neural net accelerator. Basically, we build in-house so that we're able to actually accelerate this with what we need. And I kind of just said that in like one sentence, but it's an incredible amount of work actually happening in the background just to make this thing run fast enough in the car.
Okay, thank you. So what's the next? Is there any idea?
Yeah, so the next idea is that I would say that basically the occupancy thing is really just like building these features for the world model. We eventually it's not gonna I don't think we'll explicitly be driving on top of that. So these features give us this 4D understanding of the world. And I think the next steps, a lot of the next steps will be really just like on the application level. How do we derive different applications in a very lightweighted way to represent different scenarios?
Okay, thank you.
Yeah, hi, Phil. Thanks for the great talk. So people are now very confident in the foundation models, especially after ChatGPT comes and solve everything. So people are more and more confident in these foundation models, especially how they will solve the autonomous driving task. So I'm curious about how can you quantify the data distribution for the foundation model in a driving task? As you mentioned, there are many factors in the driving, dynamic mode, static object, and also the lane factors and the different classes. So as you mentioned, when you get more data, you will determine whether the data is real in our current data, and we fit into our model. So I'm curious about how can you quantify whether the current data is real, or whether the data is valuable for the retraining of our model.
Yeah, that's a good question. Yeah, so I guess the data is basically used for whatever we need, right? So what we do is that we build a very good, there's two, I would say there are two sets of this for this. First is that we have a very complicated eval system to actually capture what is actually required for driving, right? So basically we're not building data for the sake of building data. We're building this data set to address problems. So we need to really measure our progress in terms of different scenarios so that we know which one is working well, or which one is not working well. And sorry, I lost my channel, sorry. And on the flip side, it's also there's this scaling law basically has proven to be very well done with the language model community, right? So what we also look at is that we're applying scaling law to video module as well, right? So to vision models. So how do we basically build a model at what point the model the data is big enough, right? And whether data is about or model is about right? So obviously because this runs in an embedded system in real time, so you cannot just naively scale up the model. So usually what we do is that we basically figure out what the model, what is the best size of the model that is runs in a car, and then we scale that according to data, according to compute, and according to different parameters to figure out what is the best combination. And while doing that, usually it gives us a very good idea about how the data quantity and distribution.
Yes, thanks for the answer.
Thank you.
Hi, thanks for the great talk. So I have some questions regarding deploying transformers on vehicle. So actually, transformers, we have like we basically find transformers are much more difficult to actually deploy. We are not just talking about academic here. We're actually talking about engineering, and to build a product, actually you need to make everything real time on the vehicle, and the hardware perf is. I think transformer operators create a lot of difficulties here. I'm pretty sure you. So I wonder if you could share some insight, and also I wonder like. Because right now, at least for camera-based perception, a lot of the state-of-the-art research were also like purely CNN based. So when you are building the product at Tesla, do you find that actually there are cases or there are insights where there are something that CNN simply cannot do the same good job as transformer, that you are willing to pay the cost for deploying the transformers? So maybe generalization at scale, or maybe like some others. That's my question. Yeah, thank you.
Yeah, so absolutely, deploying transformer is not very straightforward, I would say. So we actually goes to the previous question where we have an in-house neural net accelerator, which actually give us a lot of advantage, because when we build this chip, we don't have to worry about somebody else has to use this chip, right? We only build this for our own application, which obviously transformer is a big part of that. So we have a very good deployment team, actually work very hard on how to optimize this for deployment. And so far, I think initially it was quite challenging, but once we get working, it actually runs incredibly fast with our computer. And we also did a bunch of study for CNN versus transformer as well. And for us, it's that, we're not, we don't really worry too much about the philosophical debate of CNN versus transformer. We just use whatever runs fast and also does the job. And transformers obviously scale very well with the number of parameters, right? But we are, because it's a real-time system, so we're also not going that route to just like go from that. And when the parameter counts are lower, sometimes, certain CNN actually does better than transformer, I think, highlighting, complex, for example. And we definitely kind of try to take advantage of both and put together to build such a network.
Thank you.
Okay, thanks for the talk. I'm just talking a little about some challenges for generating occupancy map right there.
Mm-hmm.
So you, I guess I saw there some, you consider some night vision or some low light vision considered right there. But I'm just wondering if you consider some adverse weather conditions and contaminations on the sensor or something like that, then that make you very challenging to generate occupancy map right there.
Absolutely. Yes. So those are definitely the most challenging scenarios for us, right? So basically our customers drive everywhere, and a lot of places at different season with very challenging, scenarios. I think I probably have seen more adversarial weather events probably than anybody in the room here, just like all over the world, and we have to deal with all that. And on one side, that the fortunate thing we have is that we have tons of data from those, and we're able to actually targeting those problems specifically, solve them one by one. On the other side, definitely on the modeling side and the ground truth generative side, I would say most work is actually spent on dealing with such scenarios. And the normal sunny day driving scenario is actually quite straightforward to do. We usually don't have any engineer in the loop. You get a clip back, you run, it just works. And most of the time and the effort we're spending on is actually for all these adversarial scenarios.
Means that on Tesla, under studying about how to tackle, how to deal with that weather condition right there, are you still studying about that part for FSD?
Yeah.
So now you are developing that to handle those kind of bad challenge condition right there.
Yeah. I mean, so what we do is that the ones we already, for example, you can drive FSD in snowing days, in foggy days, for example, it works just fine. And we also we gradually move to even, there's always long tail events we try to solve, right? So if you drive Tesla, you'll notice that sometimes it will tell you whether it's degraded, so certain functionality is not working as well as expected. So that is also very important to have a good understanding of what you are capable of doing and what you are not capable of doing, and to ensure the safety. And in the long run, obviously we'll have to solve all this problem. Thanks.
Hi, in your demo, it seems that you created the ground truth, and it seems that only the static objects are created. Do you create the ground truth of the moving objects?
Yes, absolutely. Well, moving objects is a big part of the driving. Yeah, we'll have that too.
It seems that creating the ground truth of moving objects is difficult. Could you explain how the difference of the creating process?
Yeah. So I guess it's a bit of a history here, where when we started, we only do moving objects, right? Because those are more relevant for driving. And so we actually, I think it's a fairly common approach among all community that how we model moving object. We started by just doing a cuboid, right? Just like fit every car into a box, and then but then gradually we realized the problems such as the articulate bus ones we shown here. So we had to actually model the exact shape of the objects. And a lot of them are done basically through what we call offline tracker. Basically, we take all the videos back from our cars, and then we process offline to figure out what is going on. So they usually involve with three different things. First is that we have kind of like traditional robotics algorithm to use to help process the temporal information. Second is that because you have future information available offline, right, you're able to go forward and backward to actually create a ground truth that is much better than what you see in the car in real time. The third is that we also build large offline models to do this. So the models we use to run the offline ground truth generation, especially for moving object, are much bigger than one we run in the car because it runs offline. We're actually able to do that. So usually, so that's the way how we get a really good ground truth for moving objects.
Thank you.
Okay, so due to the time, maybe let's thank Phil again.